As I mentioned, start filling in all this information. In just a second, I'll scroll up so that you can see the bottom portion.
Zero, or for the white. Like, just like, we actually,
This one here,
is that the one circle on the decrease? That,
this one here?
yeah.
Yeah, that's a zero. Yep, there was a misprint, it should be a zero.
Okay, I think we're probably done with the first four, so I'm just gonna slide this up a little bit. Okay, I'm now going to move on to the second page. If you have not finished anything on the first, just let me know after notes and I will give you this copy so that you can write the rest down. Notice I have scratched those bottom two out. Don't worry about those. As soon as we get to that stuff in the later days lessons, I will be sure and go over that in detail. Don't worry about it for now. Okay, let's move on. And here's how we're going to move on. Let's go back here. I'm just going to, now that we've written all this stuff down, rather than explaining every single one, and then that's exhausting all the mental energy we have for today. Just going to give you a brief look at what all this stuff kind of means. Okay, here they had you select, is it an even, odd, or neither function? Degree function is primarily what they're talking about. Easy way to be able to tell if you're looking at a graph is look at where the graph is pointed. This one is pointed that way and that way. We're going opposite direction. So that's an odd degree. Okay. This one here is pointed, I guess you could say it's also pointed opposite directions. One's going left and right, but we're primarily looking at, are they going the same way up or down? Okay. These are both pointed up. So this is an even degree. Looking here, this is a neither because it has a definitive start. It will never go beyond that point there. And then it continues on this way forever. So that's a neither. It doesn't fit either of those patterns. If we were going south and north forever and ever and ever, your domain and range is going to be all real numbers, negative infinity, positive infinity. But if it's not going south and north forever and ever and ever, like this one here, the absolute value. Remember, domain are all x values from left to right. This graph is going to continue to expand from left to right. Therefore, our domain is all real numbers or negative infinity, positive infinity, but range are all of your y values from bottom to top. This graph will never go below that point, which is 0, but as you can see, it's going to continue shooting up from there forever. So the range would be 0, infinity. In behavior, that's another one that's just kind of weird. I'm going to use both of these examples to describe in behavior. So our graph consists of x values and y values at any given point on the graph. As our x values are decreasing this way, this is where x is getting smaller. Notice what your y values are doing. They're also decreasing. So as x approaches negative infinity, y is approaching negative infinity. Here, as our x values are getting bigger, our graph is getting bigger also. It's climbing. So as x approaches positive infinity, y approaches positive infinity. Okay, right here, this one's a little different. As x is approaching negative infinity, as we are getting smaller, what's the graph doing? It's going up. So as x approaches negative infinity, y approaches positive infinity. And here, as x approaches positive infinity, what's your graph doing? It's shooting up that way too. So as x approaches positive infinity, y also approaches positive infinity. This one right here is a good example of increasing and decreasing. Here's how you find out which one is which. I guess I'll start here first. This is a good one. Wherever the leftmost point of your graph is, just take your pen, pencil, what have you, writing instrument, finger, that's fine too. From left to right, just follow the graph. Looks like I was going up the entire time, right? I was going up the entire time. So it's constantly increasing from negative infinity to positive infinity, not decreasing. Here, same pattern, left to right. Looks like I'm decreasing, boom, to that point. So negative infinity comma 0. And then from that point, 0 to infinity, we're increasing. And next, one-to-one function. You want to perform 2 tests. Vertical. It would pass the vertical line test. I didn't cross that graph more than once. And horizontal. If I did the horizontal line test, it would only cross that graph once. Therefore, it is a one-to-one function. This one, that passes the vertical, but it would not pass the horizontal. Therefore, it is not a one-to-one. If there's any questions beyond that, talk to me after notes. I'd be more than happy to explain other examples. Okay. Actually, right here, radical. In parentheses next to it, write square root. Okay, that's what I thought. I knew it. Okay. Here, right above it, maybe, right? Reciprocal. Hear me say this. I'm going to say it. You hear it. Okay. Your Delta Math assignment is primarily page 1, page 2 of today's notes. And by primarily, I think just about everything. Okay. Now, let me warn you. This Delta Math assignment is unlike any other Delta Math. Right? I know. Thank you. Is unlike every other Delta Math assignment that we've done for the most part, because it only gives you one shot. But as long as you have this, you have the answers. It's kind of like an open note test or quiz. As long as you get 70 or higher, I'm going to give you a 100. And every student that has taken it up to this point has gotten a 70 or higher. It's easy. Okay, super easy. And I'm in the class with you. If you have a question before you hit submit, let me know and I'll say, hey, that's right. Or hey, maybe don't try that one. Let's try this one and here's why. Okay. So not too bad. All this stuff, remember these. Hopefully you do, but don't worry about it because that was not going to be on this unit at all. I don't even know why that's there. Okay, let's go down to the next page. Do it. What? I'm sorry. How can I help you? Okay, all right, moving on. Chuck paper. As I mentioned, everything on page 1 and 2, that's the bulk of your Delta Math assignment. As long as you filled in all that information, you're gonna do just fine. This stuff is also a review of Algebra 2. It's a review of Algebra 2. So here we go. Determine whether the relation is a function. If we have a set of ordered pairs, here's what you're looking for. Do your x values repeat? Here we have an x value of 0. There I have an x value of 0. No. How about no? That is not a function. If you look at example B, look at all your x values, see if any of them repeat. There are no repeating x values, therefore that would be a function. That's how you determine if a set of ordered pairs is a function or not. But right here, graphically, how do you determine if it's a function? We've already done this. Vertical L test. We already did that. Now, for example, C, D, F, and G, they want you to perform the vertical line test on each and every one of those to see if they are a function or not. Be careful with G. I know that looks like it might not pass the vertical line test, but it will. Yes. This one right here? Okay. We're about to do that in just a second. Is it a function? Is it a function? That's all it wants to know now. This is a good question. Is it a function if it passes the vertical line test? Yes. Is it a one-to-one function? It has to pass both. It has to pass both. So for C through G, it simply wanted us to figure out if they are a function. Now this one here, this section, now it wants us to determine which one of these are one-to-one, and now C is eliminated. That's not a one-to-one. That's not a one-to-one. This one isn't because it didn't pass the vertical line. This one is, that one is. So F and G. Those are one-to-one functions because they pass the vertical and horizontal line test. Excellent. Example A, state the domain of each of the following functions using interval notation. This right here, I would remember this. This is a quadratic. That might help you on your Delta Math today in case you don't know what that looks like immediately. State the domain. Well, if it's a quadratic, then your domain is going to be all real numbers, negative infinity, positive infinity. No. I think so. Maybe. I don't know. I don't know. If you do and you don't know how to do it, I'm here. Here, how do we find the domain of this particular function? Well, we have to restrict the domain because if you'll notice, we have x on the bottom of a fraction, meaning there's something x cannot be. Does anybody know what it is? It's 5. Great. The way you mathematically determine that is take whatever your denominator is, set it equal to 0, and then solve. X cannot be 5. If it was, then we have a 0 in the denominator, and we can't have that. How do we write that in interval notation? As such, all real numbers from negative infinity that approach 5, parenthesis, because a parenthesis means it doesn't include 5. It includes everything up to 5, but not 5. Union, we can have numbers from a little bit after 5, but not 5, all the way to positive infinity. So if there's restrictions, positive and negative, that's one way you can do it. Okay, over here. Let's see, what can X not be? Can X be 9 here? Be careful with this one, can it?
Yeah.
It can be. Because let's think about it. 9 minus 9 is 0. And can you take square root of 0? Yeah, you can. So it can be 9 here. Here's what it can't be. It can't be anything less than 9 because we would have negative numbers. We don't want that. Okay. So we could just simply do bracket 9. It can include 9 and all the way to infinity. See what you can. Okay, next, state the domain and range of each of the following relations using set and interval notation. Yes, go ahead.
You said like when you put the 25 or that number can't be included.
Correct.
So when you use it on infinity, even though you say like up to infinity.
Yeah.
Does that just mean like infinity so big?
Can't put a cap on, can't stop it. It'll never stop. Yeah. That's one way of looking at it. Infinities get parentheses. Yes.
Why can't, why did you go like a union?
Okay, so for union here, notice we had everything before 5 and everything after 5. Here, we can't have anything before 9, period. So we don't need the union here. Practice. Because here's another way. Okay, you could just plug it in. Let's say here I plugged in -4. Did the math, would get -9. I can do 6 over -9. Sure, no problem. Here, I plugged in -7. I'd have -16. Can you take the square root of -16? No, you can't. So that's one way you could figure it out. You can't. Can't take square root of any negative number, at least. Right. Then we're dealing with imaginary numbers, and that's another lesson. Would you like to review imaginary numbers? I didn't think so. Okay, let's move on. Thank you, everybody. Thank you. All right, let's move on. Lollipops for everybody when I'm done. Okay. State the domain and range of the following relations using set and interval notation. Set notation is confusing. We will have a lesson at some point that really goes over that. Not today. So whenever we get there, we'll make sure we really skip that. We're not doing set notation. Let's move on. Yes. Yeah, sure. Go ahead. Did that. All right, this right here looks a bit more than it is. It's really not too bad. X-intercepts, Y-intercepts. You can just look at the graph, figure out what those are. I'm not going to write them down as ordered pairs, but we have an X-intercept there, -4. X-intercept there, -1. Another one there at +1. Another one there at +3. That was easy. Looks like we have a Y-intercept when Y is 1. Local maximum, or maximum, but I'm just gonna say maximum. Local maximum means in our graph, do we have any peaks? We have one here. You only need the Y value. We have a peak where Y is 1. Do we have an absolute maximum? Meaning, do we have a point in this graph where we will not go any higher than that graph in that point? No, this goes on forever, never, never. So we don't have an answer for that one. It goes on forever. Here, local minimum. We have 2 minimums. There and there. You only need the Y values. Do we have an absolute minimum? Do we have a point on this graph that will never go any lower than that? Yes. So -4.5. Intervals of increasing, decreasing, continuous. That's going to be the next lesson. We'll do that when we get there. Okay. None of that stuff is going to be on today's stuff, but we will be seeing it next class. So let's just worry about it next class. Okay. Here. Even degree function. Here's how you can tell whether or not you're dealing with an even degree function. We've already covered this by looking at a graph. even degree functions are either going to be pointing up, up, or down, down. And I'm going to put a positive underneath that arrow and a negative underneath that arrow. And I'll show you why in just a second. Odd degree functions are opposite directions, either down, up, or up, down. I'm going to put a positive at that last arrow and a negative at that last arrow. So it has given you a graph and it asks for, hey, what type of degree are we dealing with? Well, these arrows are going opposite directions, so it must be odd. This last arrow is pointed up. Therefore, our leading coefficient is positive. That's why I put positive and negatives underneath the last arrows that I just gave you, those examples I just gave you. In behavior, as x approaches negative infinity, y is also approaching negative infinity. And as x approaches positive infinity, y is also approaching positive. This example here, your arrows are pointed in opposite directions, so it must be odd. Notice the last arrow is trending downwards towards negative infinity. So we must have a negative leading coefficient. In the behavior, look at the left portion of the graph. As x approaches negative infinity, it looks like y is going up. Look at the right side of the graph. As x approaches positive infinity, it looks like y is pointed to negative infinity, down. These even degrees are pretty easy. I think they're easier. Both are pointed up, so it must be even. How about I say this a different way? They're both pointed the same direction, so it must be even. Since they're both pointed up, it must be positive. Up, up, positive infinity, positive infinity. These two arrows are pointed in the exact same direction, so it must be even. They're both pointed down, so the leading coefficient must be negative. In behavior, negative infinity, negative infinity. And then the last thing that we're going to do today, determine the end behavior. Well, if it gives us polynomials, not a graph, here's how you figure out what we're dealing with here as far as end behavior is concerned. Notice that each of these examples, it gives you, looks like for each example, there's two exponents for each one. You're looking for the biggest exponent. Your biggest exponent tells you what type of function we're dealing with. Our biggest exponent is 4. That is even. So our options for end behavior are either up, up, or down, down, based on the leading coefficient. The leading coefficient, the number in front, is a positive number. So that would eliminate that option. We must be up, up. First arrow is pointed up. So in the first spot, put it at infinity. The second arrow is pointed up. So in the second spot, put infinity. Example B. Looks like we have an exponent of 5 and an exponent of 4. We want the biggest one, 5. That is an odd number, so our arrows must be going in opposite directions, either down, up, or up, down, based on the leading coefficient. Now we can determine it. Looking in front of the highest exponent, we have a negative number. So our last arrow has to be trending towards that direction negatively. So we can eliminate that option. The first arrow is pointed up, so in the first blank, put positive infinity. The second arrow is pointed down, so in the second blank, put a negative infinity. And on the last page of this of these notes, that is all stuff we're going to be doing next class. So we'll worry about it next class.